Hey everybody, thanks for checking out the channel. When Reefs RC first debuted their shocks, they didn't really catch my attention. Their marketing department spent a lot of time focusing on the preload adjuster, which is cool, and their keyed shock cap, which is just okay. However, I learned they have two very cool things going on that deserve a closer look. On this channel, we look at the science behind our grown-up toys. There is a really great crawler shop in Pocatello, Idaho called OCD RC, and it's run by Jaron Allred. Link in the description. They do tons of internet custom builds, so check them out if you want something super high-end, custom built with an OCD level of attention. Anyway, I was passing through, and Jaron asked me if I had seen Reefs shocks and handed me a pair. What you don't really see online is how slim they really are. They are small, which is awesome because the front shocks can get in the way of your steering at high angles. And slimmer is lighter. Reefs, now you have my attention. Secondly, after talking to world champion and shock designer Wyatt Mellon at Proline by the Fire, he explained to me his damping philosophy. And now we've got a very interesting product to look at. Shout out to Reefs for providing the shocks and being open to my honest teardown. Wyatt told me that before this Reefs shock, he was using 10-weight oil in more common 10mm piston shocks like DravTech and Traxxas 2660, but he wanted even lighter, faster damping. He describes his tuning response as floppy bacon. So that's how the damping profile of this Reefs shock originated. You can learn everything you never wanted to know about oil weight in this video. Typical oil weights for common 10mm piston shocks is about 30 weight. Available oil weights for RC range from 10 to 100 weight. That's about 100 to 1200 CST. With this new open bypass piston on the Reefs shock, also known as a free bleed circuit, the average weight now shifts to about 50 weight. So you have more options on the lighter side or the faster side of available oils. With this piston design, drivers like Wyatt and myself can now fine-tune down in the 15, 17.5 oil weight range. If you want to determine which oil is best for your rig, don't ask your buddies or the internet. You'll want to determine it for yourself, and I have a video that explains exactly how. Let's take a closer look at these Reefs shocks. All right, let's see what we got here. These come in both a 90mm length, and I have the 80mm length, and they come in a longer 100mm length. And they also have colors for just the 90mm length as of the time of this video, but I'm sure they'll make more as the shocks get more popular. This orange looks absolutely terrific. These come completely assembled, which is a nice touch, and they're packaged nicely. All right, so they're really small diameter is what I like. Just to compare, this is what a deluxe looks like diameter-wise. Let's compare the two. The fat end of a deluxe is going to be 14 millimeters, whereas the fattest part of this Reefs is only 11, and it's all the way down to 9 in the middle here. So if you've got turning clearance issues on your vehicle, this may just line up really well with the clearance you need. So let's take one apart. Now, if you haven't seen this spring removal trick, it's one of my favorite tricks. I didn't think of it, but you can take off your spring without taking your shock apart. We are going to take this apart, but you don't have to take it apart to change your spring rates if you just twist it off like this. You can get 3 different spring rates, and there's actually 2 different lengths for the longer shocks and the shorter shocks. They don't publish what the exact spring rates are, but I will in another video show you how to measure very easily what spring rates are if you have a bunch of random springs that you don't know what their rate is. They do make 2 lengths, the longer one and the shorter one. And the longer ones, I believe, are going to be softer than the shorter ones. And you can theoretically put a longer spring on the shorter shock if you wanted more preload but less spring rate. That's a topic for some of my other videos, but they do have 3 spring rates in 2 lengths. So this has a built-in preload adjuster, and Sharif, the founder of Reefs, is super proud of this. He talks about it all the time, and it's pretty cool. This rod end is threaded, and it has a really nice aluminum collar on it, so you can screw this up or down and adjust your preload to whatever taste you like. Now, just a reminder, the purpose of preload is to set your ride height. Adjusting your preload doesn't make the shock stiffer, it just makes the shock sit extended more. So if you've got low preload, your shock will sit more compressed. If you crank up the preload, your shock is going to sit up higher, but the total spring rate doesn't change. That again is a topic I have in this video if you want to know all about springs and spring rates, and there's a lot of confusion between preload and spring rates, so check out this video for sure. All right, so that collar does come all the way off if you overturn it, which you wouldn't want to do. You've probably got a usable 4 to 5 millimeters of preload should you want to use that. Now I'm going to take this one apart. All right, so this is a custom rod end with the preload adjuster right there. It's a really nice part. This rod end is also custom. I think you could probably put standard rod ends in here if you wanted a different length rod end. We'll explore that in a minute, but they do have this keyed into the end. I'm not 100% sure what the benefit of that is. It does keep it from unscrewing, and it does make it easier to take off this top cap when we get to that. So you've got 2 threaded ends. You've got this right here, which contains the seal stack, which we'll take apart in a second. This is a really nice touch. It doubles as the spring collar and also captures the seal stack, which is super nice. And this eliminates the circlips that you may see on other shocks that require the special pliers to put in. Not necessary on this shock. This just unscrews. But let's take apart this end first. So this rod end allows you to unscrew this. And there's no oil in it because you're going to pick the oil that's best for you. This looks like a really nice silicone. I'm going to guess it's silicone. They wouldn't tell me what the material is, which is fine. Got to keep some secrets. I'm going to guess this is a silicone seal. Silicone is great because it's very neutral. It doesn't swell with different greases and additives, and it's really squishy, and silicone often is clear like this, so it's probably a silicone seal. So there's your top cap, and again, the widest section is only 11 millimeters. And this piston is going to be the really interesting part, so let's take this out. Okay, I'll get to this in a minute. Let's take a look at what's in this seal stack here. Oh, very nice. Okay, so this looks like a silicone O-ring, but it's custom made. It's got this flange on it, which is really nice because when you put it in, you can see you've got that flange overhanging the top, and that is going to seal against the inside of this. So you've got an additional seal. Yeah, I can feel the pinch right here. So it gets almost to the end, and then there's about 1/8 of a turn that compresses that little flange. That's a really nice touch. This is definitely custom made because I've never seen an off-the-shelf part like this. The other cool thing is that this will bottom out right here, so you can't over-compress this. This pushes very gently against this flange and then bottoms out right here, so you're not going to over-tighten this. Some shocks, if you keep cranking them down, you'll eventually crush and damage the seal. So this is a really nice, this is the proper way to do it. You have a hard stop that doesn't crush your seal. So you've got that seal, This is a great way to damage your seals, pulling them out this way. All right, so that's a beautiful quad ring. Quad ring is actually basically 4 tiny O-rings melted together, so you've got kind of a clover shape if you were to cut this apart. And that gives you 2 sealing lips on each surface. So quad rings generally seal better than your standard O-rings. This could be off the shelf, although it's a perfect match to the other ones. They may have custom made this one as well, not sure. Feel like I lost a part somewhere. The center spacer rolled away somehow. So basically you've got, when this is assembled, it looks like this. You've got this nice O-ring with a bonus flange, center spacer to keep things apart, O-ring right here. Now, when I put this together, I would load this up with grease. Reefs says it's fine just to use silicone oil, so you can drench this in oil, put it together, then you've got the same oil here as you do inside the shaft. But you should never have silicone oil leaking from the damping into this body. This seal should keep it on the other side. So I like to use grease in the middle here because it lasts longer and it's smoother than silicone oil. But Reef says silicone oil is just fine. What I like to use is udder butter, and the reason why I use udder butter grease on my shocks is because it's one of the only greases that I know will not swell the seals. And that's simply because they told me that was the case. Many seal greases will have expanding additives that will cause your O-rings to swell, and they seal nice and tight, but they also get tighter and they're not as smooth. So udder butter, I know for a fact, will not swell your seals. So that's what I always use on my seals. I'm sure there are others out there, but I just don't know for a fact. You would want to ask any manufacturer whether they use seal swelling additives or not, and I recommend not using it. If you build your shock correctly, you shouldn't need to swell the seals. They should work as designed. Cool, so now let's take a look at the piston shaft. This is a hard chrome, which is a great finish. Sometimes you'll see a gold colored, which is a titanium nitride finish. Titanium nitride is generally a harder coating than chrome, but this is more than sufficient for what we're doing. I did ask Wyatt a very tough question, and he came back with the right answer. I said, what is the surface roughness of your shaft? And he said, I know, but I'm not going to tell you. And the fact that he knows is the important part, because all seals are designed to work at a specific surface roughness. Smoother is not always better. If this surface is too smooth, it won't allow lubrication particles to penetrate the surface, and it'll be too sticky. So there is a point where if the shaft is too shiny or too polished or too mirror-like, that the friction actually goes up instead of down. So I don't recommend changing the finish on any of your shock shafts. Sometimes you'll see people sandpaper them and make them smoother. That's a terrible idea, which I will explain in another video. But for today, what's important to know is that Reefs knows what the surface roughness is, and that surface roughness is designed specifically to work with their seals. And that's the level of detail that you may or may not get from all manufacturers. The way you determine surface roughness is there's something called a profilometer or a profile meter, and it basically is a little point that you drag across, and it bumps up and down on the surface and will give you an average measurement, all the microscopic bumps on the surface, and you do want to have some control over that surface roughness, especially when you're making a friction sliding surface. So good on Reefs for paying attention to that. All right, the next thing I want to talk about is this piston head. Notice how there's no circlips. There is a lock nut threaded on the end of the shaft. That's really cool because circlip pistons are kind of hard to install. You usually end up losing a couple of circlips before you get them both on there. And you also can get this play in the circlips, which I don't really love. I think this should be tighter so that your piston isn't shuddering or vibrating when it's moving back and forth. I prefer this to be tight. So these nuts keep it nice and tight. I'll take this apart. Let's see, a 4.5 doesn't fit. 5 is kind of loose. I'm not sure if that's a 5. Is this American size? Well, 5 kind of fits, okay. Doesn't have to be ultra tight. All right, so that comes off. Here's the piston head. And it looks like there's a little washer to hold the piston head on. My guess this is a 2.5. Yeah, so this is a 2.5 thread, 3mm shaft, 2.5 thread, which gives you a little shelf to hold this washer. And that keeps the piston head in place. Then you screw this on. Probably wouldn't hurt to use a drop of Loctite on this. This is a nylock nut, but nylock is reasonably effective. Loctite is much more effective. Now, let's talk about this piston head. This is a 3-leaf clover. There are no holes in the piston. Instead, there are 3 half-circle cutouts along the outside. And what that does is allows the oil to flow around the outside of the piston. And that pretty much removes all of your high-speed damping, because the way high-speed damping works is your textbook orifice plate oil flow calculations. I've done a whole video on piston damping, and basically when you've got a hole at a certain velocity, that hole tends to choke off oil flow. So that's how you control high-speed bottom outs on a buggy where you're jumping a lot. But we're not really jumping these crawlers, so they pretty much removed any high-speed damping, which is great. And that allows them to make this really small. And we're really only concerned with slow-speed damping on a crawler. Now, when I say slow-speed damping, it doesn't refer to the speed of the vehicle. It refers to the speed at which the piston is moving through the oil. And crawlers, yes, they move slowly, and also their shocks compress very slowly. Unless you're doing a throttle bump, then you might get a little bit of velocity on your shaft speed, but for the most part, you're not going to miss the high-speed damping on this. One other thing I want to check is, see how big the outside diameter of this is. So it's kind of hard to measure a 3-lobed clover. But it looks like this is right about 6.9, which is what I would have guessed. And the reason I care about that is, let's see what the inside diameter of this is. I have this little gauge here that expands and allows you to measure inside diameter. So you put it on the inside, you dial it up until it just touches the walls. Okay, so it's just scraping along the walls. I'll pull this out, measure this. I bet this is going to be real close to 7. Oh, a little bigger, 7.2. Okay, let's call that 7.2. So that's 7.2. It's going to give us a delta of 0.3. Now, the reason I'm interested in this is because most other shocks I've measured have a delta of 0.1. And then they're going to have piston heads with holes in the piston. On other shocks that have traditional piston heads, they have a real small gap around the outside. And that small gap around the outside is mostly contributing to the low-speed damping, whereas the piston holes contribute to the high-speed damping. In this clover shape, it's going to be really hard to draw. Yeah, not too bad. On this clover shape, we've got a bigger gap around the outside and these 3 holes. So this has a lot of openness, a lot of free-flowing oil from one side to the other. Now, this diameter is smaller. So let's say this is a 10mm diameter. You've got a larger circumference, a larger area around here than you do around this smaller 7mm. So they may have opened up this gap to better match what a larger piston might do. I feel like I'm probably starting to lose you here at this point. The bottom line is there's a lot of free bleed. There's a lot of area both around the diameter of the piston head and through these 3 holes that allows oil to flow through. And that's why you would start with a heavier oil on a reef shock than you would on other shocks, because there's so much bypass or free bleed going around the piston. And I think that's a great thing. For people that want real light damping, 10, 15, 20 weight oil, this is the piston for you. But you've still got 70, 80, 90. You can still get plenty of thick, heavy, slow damping if you've got a high spring rate, heavy vehicle. This will also accommodate heavier weight oils for vehicles that might need it. So I think this is a great concept because it gives you better options for damping oil, both on the lighter, faster side, and still has plenty of options on the slower, thicker, heavier oil side. Let's do a quick weight check. These are both 90 millimeter shocks, and they do have oil on the inside. 13 versus 13. Wow, I'm kind of surprised. I really thought this thinner shock would be lighter, but seems like they're pretty close in weight. The big advantage is the much smaller diameter. And the last thing I want to point out is you don't have a ton of options for the eyelets. This is their shortest 80 millimeter shock. It's got 15 millimeters of stroke. A similar shock from Deluxe would also be 80 millimeters and has just a little over 15 millimeters. So they're pretty comparable. One of the things that you can do on other shocks is get these offset shock caps, which will make your shock shorter. And if you really want to go crazy, you can also get offset eyelets and build your shock crazy short. I don't necessarily recommend this unless you have a very, very challenging packaging situation, but I do believe that Reefs is probably going to work on a way to make this shock shorter with some different rod ends, but we haven't seen anything yet. So for now, we've got to make 80 millimeters work. So this is the point in many YouTube videos where a YouTuber would go out on the rocks, do a little driving, and say how great the shocks work. Well, I don't do that because it would be a disservice to you. There are 2 things that are really hard to quantify in real life, on the trail and on the rocks, that I generally don't test: tires and shocks. Unless I can provide a clear A-B comparison that demonstrates an advantage or disadvantage, I'm not going to simply drive around and draw conclusions. You don't come here for opinions or feelings, you want facts and numbers. I've seen professional athletes and professional shock tuners make this mistake all the time. If you want to draw conclusions based on your driving or riding, you need to create a repeatable and controlled test environment. If you just put a part on your rig and go drive it, you cannot make any conclusions that meet a level of scientific rigor. To do it right, you need to do multiple runs on a repeatable section, back to back, with both parts being compared, then back to back again with multiple drivers, and you would need to do it blind. I don't mean blindfolded, but blind meaning you, the driver, do not know which option you are driving. And ideally, the person setting up your vehicle would not know which option they gave you to drive. That eliminates all bias. I assure you, it's much harder than you think. I've had professionals downright refuse to do blind testing because they believed they didn't need to, but in reality, I suspect they just didn't want to learn that they may not be as sensitive as they thought they were. But I'm going to take one measurement and see what the difference in damping force is. Let me start by saying that the only correct way to measure shock damping is with a speed-controlled shock dyno, which is quite expensive and I don't have one. There are only 2 companies in RC that I know of that have shock dynos, MIP and Soda. What I'm about to do is not the right way to measure shock damping, but it will show us if there is a big difference in slow speed damping or not, and that's about all it's going to show. So I'm going to attempt to get a force reading on what the difference in damping force is between a more traditional 10 millimeter shock and this Reefs with the bypass clover-shaped piston. Now, let me say that first that This is absolutely not the right way to measure shock damping. Shock damping is generally velocity sensitive, meaning the faster you push it, the higher the damping force. And it's really impossible to apply the force at a constant rate by hand. That's why shock dynos are very expensive. You have to impart a constant speed. Now, it's easy to apply a constant force, but a constant speed is much harder to do, especially at home. That's why shock dynos are $10,000 or more. In this case, we're just looking at low speed damping. And if you want to know more about how piston head damping works, check out my video here that talks about all the different variations on piston heads. And I talk about high speed and low speed damping. For a crawler, we're really only interested in low speed damping, which is convenient for this test. So what I'm going to do is push on this as slowly as I can and just measure the force. It's just going to give us an idea how different these two shocks are with the same weight oil. I went and bled both of these with 50 weight oil. It's kind of in the middle of the available range. You can get oil from 10 to 100, so 50 seems like a reasonable place to measure. Another thing about these simple shocks is there's always a little bit of rebound in them. See how there's a little bit of return there? That return is coming from the rubber bladder on the inside and the air trapped behind that bladder. And if you want to learn more about bladder tuning, I also have a video on that. The Reefs does not have a bladder, so it's an emulsion shock, but there is still air trapped inside. If there weren't, this hydraulic piston would lock, it wouldn't move. If it's 100% fluid with zero air inside, the piston can't move. Fluids are considered incompressible, and that's how hydraulic pistons work that drive heavy equipment and other things. So in order for this shock to work, you've got to have some air inside. And that's the very definition of an emulsion shock. So there isn't a bladder separating the air and the oil. Normally the air bubbles will float to the top and it won't affect the piston. Or in the case of a buggy, a true emulsion shock, the air will always be mixed up with the oil, creating an emulsion. And that emulsion is kind of more like a foamy oil, and your piston head is designed to work with that foamy oil. But this is never going to get foamed up in a slow-moving crawler, so what's going to happen is that air bubble is going to float to the top and sit there out of the way where it's not bothering anybody. And my point is that air bubble is going to provide a little bit of rebound. You're compressing that air, making an air spring. Now you can bleed this so there's less of a rebound, but I'm not too concerned about that right now. What I want to do is I'm just going to measure the force kind of at the beginning of the travel where there's not any influence from the spring. And I'm going to do the same here. I'm just going to measure kind of at the beginning. And we're just going to get a basic slow speed force number to kind of give us an idea how different these shocks are. So I'm just going to screw this in here loosely, set this in here loosely so the shock is kind of free on both ends. It's not going to get bound up. And I'm just going to push on it real slowly and kind of read the number. Looks like it's about 9 or 10, 11. Okay, I want to keep it in the beginning of the stroke. So I'm going to do this multiple times. Looks about 9 to 10. So it starts off about 6. So I'm going to call this about 7 to 9. And then I'll try a Reefs. What we're going to do, again, we're just going to measure just right here at the very beginning of the stroke where it's the most linear and the least influenced by any rebound from the air spring trapped inside. So once we start to get past 50%, you can see it starts to ramp up real quickly. That's because I left air in there, and you can bleed it more neutral than I did. So I'm just going to measure, I'm just going to take a reading from the beginning of the stroke. And this is looking like about 3 or 4. And I'm going to go back and do the orange shock one more time. So it immediately starts about 6 to 8. And you can see this force ramps up as well as you go deeper into the stroke because of that internal spring. So the shock's not even moving right now, and this is how much spring force is pushing back on it. There's zero damping force right now because it's stationary. This is the spring force that's on top of the damping force when it's moving. So I'm going to revise my numbers down just a little bit. It's about 6 to 8, I think, is the range I'm looking at. So you can see these both have 50 weight oil, but the damping force from the damping alone is quite a bit different. If you're coming off a Deluxe or Traxxas shock and you use 30 weight there, Wyatt actually told me that 50 weight is a better starting point on a Reef shock. That's about a 50% difference in oil weights. Now, if I average out my simple force measurements, I was getting about a 60% difference, so I'd say that checks out. Reefs does have a lower initial damping force starting point. I think these Reef shocks could be a terrific option for your crawler. They are small, lightweight, have very light damping force, have virtually no high-speed damping, all of which are great advantages. The only drawback is they have less eye-to-eye length options because of the custom rod ends on both ends. And they don't have offset shock caps just yet if you wanted to make a really short shock. Just to be clear, the only thing that offset shock caps offer is a shorter length for packaging. And offset caps are actually a performance disadvantage, which I will explain in an upcoming video. Also, only the Reefs medium 90mm length has color options at the time of this video. Fortunately, orange is one of those colors. I do plan on running these long-term on my next build, but only after I build a negative spring version of it. So stay tuned for part 2, where I completely destroy their design and reimagine it for my evil purposes.